To calculate the feeder protective device size using an inverse time breaker for a 240-volt three-phase delta system with multiple motors, including a 50-horsepower motor with a 5-minute intermittent duty rating, you need to consider the full load amps of each motor and apply the relevant factors according to the National Electrical Code, NEC. The key point is that the duty cycle adjustment primarily affects the conductor sizing, not the breaker sizing. The breaker must be able to handle the motors running continuously, even if some are intermittent duty loads. Here's a breakdown of how to approach this calculation. Firstly, identify the full load amps for each motor. The question provides the following full load amp values. The 50 horsepower motor has 130 amps. The 15 horsepower motor has 42 amps. The 10 horsepower motor has 28 amps. Secondly, apply the NEC rules for sizing the feeder breaker. According to NEC 430.62, the feeder overcurrent protection device shall not be less than 125% of the full load current rating of the largest motor plus the sum of the full load current ratings of all other motors in the group. This ensures that the breaker can handle the inrush current of the largest motor without tripping, while also protecting the feeder from overloads. Thirdly, calculate the contribution of the largest motor. In this case, the largest motor is the 50 horsepower motor, which has a full load current of 130 amps. Multiply this by 1.25, which is 125%, to get 162.5 amps. 130 amps times 1.25 equals 162.5 amps. Fourthly, sum the full load amps of the remaining motors. Add the full load amps of the 15 horsepower and 10 horsepower motors. 42 amps plus 28 amps equals 70 amps. Fifthly, add the results from steps 3 and 4 to determine the minimum breaker size. Add the adjusted full load amps of the largest motor to the sum of the full load amps of the other motors. 162.5 amps plus 70 amps equals 232.5 amps. Sixthly, select the next standard breaker size. The NEC requires using the next highest standard overcurrent device rating if the calculated value does not correspond to a standard size. Standard breaker sizes are defined in NEC 240.6. In this case, 232.5 amps is not a standard breaker size. Therefore, you must choose the next higher standard size. Common standard breaker sizes include 250 amps, 300 amps, 350 amps, 400 amps, and 450 amps. Seventhly, verify the breaker size against the conductor ampacity. Ensure that the breaker size does not exceed the ampacity of the feeder conductors. A conductor ampacity must be equal to or greater than the calculated breaker size. Refer to NEC Table 310.16 for conductor ampacities based on conductor size and insulation type. If the initial breaker size is too large for the conductors, you must increase the conductor size accordingly. Eighthly, consider the intermittent duty of the 50 horsepower motor for conductor sizing, but not for breaker sizing. As correctly pointed out, the 5-minute intermittent duty rating of the 50 horsepower motor affects the conductor sizing, allowing for a possible reduction in conductor size based on the duty cycle. However, it does not affect the breaker sizing. The breaker must be sized to handle the continuous running current of all motors, regardless of their duty cycles. Ninthly, review the options. The available options are 300 amps, 350 amps, 400 amps, and 450 amps. Based on the calculations, 232.5 amps is the minimum required breaker size. The next standard size above this is 250 amps. However, none of the options provided are 250 amps. The next highest standard size among the options is 300 amps. Therefore, the selection process involves ensuring that the chosen breaker size meets the minimum requirements calculated from the motor full load amps and adheres to NEC guidelines for standard sizes and conductor ampacity. The duty cycle of the 50 horsepower motor only influences the conductor sizing, not the breaker sizing. Given the options 300 amps, 350 amps, 400 amps, and 450 amps, and the calculated minimum of 232.5 amps, The 300 amp breaker is the smallest standard size that meets the requirement. However, let's re-examine the calculation to ensure accuracy and address the provided options more directly. The adjusted full load amps for the 50 horsepower motor is 130 amps times 1.25 equals 162.5 amps. The combined full load amps for the 15 horsepower and 10 horsepower motors is 42 amps plus 28 amps equals 70 amps. The total calculated amps for the feeder breaker is 162.5 amps plus 70 amps equals 232.5 amps. Rounding up to the nearest standard breaker size, we look at the available options. Option A is 300 amps, option B is 350 amps, option C is 400 amps, and option D is 450 amps. Since 232.5 amps is the minimum and we must choose the next standard size, 300 amps is the closest and acceptable size from the given choices, provided the conductors are rated for at least 232.5 amps. If the conductor selected based on the duty cycle and other factors have an ampacity of at least 232.5 amps or more, then a 300 amp breaker would be suitable. Now, considering the continuous operation requirement for the breaker, we must ensure it can handle all motors running simultaneously. The total full load amps of all motors is 130 amps plus 42 amps plus 28 amps equals 200 amps. This is the continuous load the breaker must handle. The 300 amp breaker can handle this continuous load with a safety margin. If the conductors were sized smaller due to the intermittent duty of the 50 horsepower motor, they must still have an ampacity of at least 200 amps for the continuous load, and the breaker must protect them adequately. If the conductor ampacity is close to 200 amps, using a slightly larger breaker such as 350 amps might provide a better safety margin and allow for future expansion. The NEC allows for some flexibility in breaker sizing to accommodate motor starting currents and other factors. However, it's crucial to balance protection with avoiding nuisance tripping. Given the specific options provided, and assuming the conductors are appropriately sized for at least 232.5 amps, the 300 amp breaker is the most suitable choice. However, if there is any concern about nuisance tripping or future load increases, a 350 amp breaker could be considered, provided the conductors are rated accordingly. In summary, the selection of the feeder breaker involves calculating the minimum required size based on the motor full load amps, considering standard breaker sizes, ensuring conductor ampacity is adequate, and accounting for continuous operation requirements. The duty cycle primarily affects conductor sizing, not breaker sizing.